The OSI network layer. The primary responsibility of this layer is end-to-end routing. Seamless packet delivery from a source to a destination is accomplished through the use of many processes and tools. In this nugget, we're going to look at two of the most important. First, logical addressing, and then fragmentation. We will begin our conversation on logical addressing with a look at something that's very familiar. First of all, we see here a representation of an envelope. Inside it, a message, a piece of mail. What I want you to pay close attention to is I have the common addressing here. First, a source name, a source street number, and a source city, and then a destination address, again complete with a name, a street address, and a city address. Let's take a look at our diagram below. Illustrated here is the name of the individual sending the mail, the street address of the house, as we see here, and then the city address that this house resides in that I see here. So, to further our analogy, let's say that a postman picks up our mail at our mailbox here. It's delivered to the local post office. At this point, we have to trust the U.S. Postal Service to get it from one post office at the local site to the destined post office. And this is done by using the city address that it's destined for. So going from Los Angeles post office to the Dallas post office, they use that portion of the address. Once I'm within the city, the next address that is used is the street address, and I see that here. I pinpoint the location of the house with the street address so that a postman can pick up that message from the post office and deliver it to the house. Once inside the house, the name comes into play, and it says this specific message is destined for John Smith. So here we have a representation of logical addressing within the United States Postal Service. In short, the result of logical addressing is a unique identifier for every object that can send or receive a message within a specific network. Now let's look at logical addressing in respect to the network layer of the OSI model. As you can see, I have two options at this layer, IP and IPX. Now I understand there are many more protocols available at this layer, but the scope of the CCNA only includes IP for the TCP/IP protocol and IPX for the network protocol within the network layer of the OSI model. Now let's see how our model of the U.S. Postal Service and its use of logical addressing maps to our Internet model and its use of logical addressing. First of all, we're going to have a source and a destination address as we had on the envelope, and the source address in the network model will include all that you see here, and the destination will include what you see on this end. Let's see how they map. The first thing you have is a name. The name is analogous to a MAC address. Now this MAC address will be explained further in the data link layer, but I'm going to include it here for a source of reference. The next line we see is a street address, which is most like a host address in the networking world. And then we end up with a city address, which is analogous to a network address. You see the same thing on the other side, a name to a MAC, a street to a host, a city to a network, and you can see the representation on the envelope. John Smith, MAC address. The street address is a host address. The city is a network. Alright, I'm going to use an IP example to show us how the different parts of logical addressing are derived in a real-world scenario. Here we have a representation of a network, here, with a source of N1 as a computer and a destination of N2 as a computer, a couple of routers, and the Internet in between. Again, like in the analogy with the United States Postal Service, I have to find unique identifiers for my source and my destination object in this network. What do I have that I can do that with? I have an IP header that you see here. Now, while I have quite a few fields in the beginning here, in fact these first three sections, they are useful in networking, but for the sake of our analogy, we really are only going to use the IP address of the source and the destination IP address to fill in our envelope fields that we saw earlier. Let's fill these in. We're going to have a source IP address of 192.168.1.253 and a destination IP address of 192.168.2.253. Now at first glance you might be somewhat scared because you're thinking, three of these octets are the same and only one differs. That one difference is key in what we're doing, and we're going to explain that in our next section where I look at how we're going to divide this one number into both our host and our network numbers. Alright, you see these addresses represented here, source and destination. Before I show you how to divide an IP address into two distinct parts, let me start by giving you an IP address definition. Now understand that we're going to cover IP addressing in great detail in a later nugget. So for right now, we're going to give you a simple definition, and it is: an IP address is a 32-bit binary number represented in decimal form. This is going to be important in the way that I derive two pieces out of one number. So let's look at the conversion, looking at our decimal form of an address and what it truly is in binary. What I've done is I've given an IP address of 192.168.1.253. And if you recall, in our last whiteboard, that was N1's IP address, or the IP address of our source. So let's break that into decimal form. I have a 192 in my first octet. Why do I call that an octet? Because it has 8 identifiers, or 8 places within our binary representation, and you see them here. There's 1, 2, 3, 4, 5, 6, 7, and 8. Each has a numeric value associated with it. Now whenever we're going to represent anything in binary form, we have to understand that there's two states. A 0 equals off, and a 1 equals on. So as we use those, when we represent our decimal number into binary, you'll see how this works. First of all, I'm going to say my binary representation of 192 is 1, 1, 0, 0, 0, 0, 0, 0. Don't worry, I'm not going to leave it at that. Let me explain how I got that. Again, 1 is on, 0 is off. So, in the 1's place, because it is off, it's simply a 0. In the 2's place, it's off as well. 4, 8, 16, 32. Those are all set to the off position. Now I have my first on position, 64, and the next one is on as well, which is 128. What I do at this point is I simply add all of these values to come up with my decimal number. And in doing that, I have 128 plus 64 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. And what does that equal in a decimal form? 192. Let's go on to 168. What I have here is a binary representation of 1, 0, 1, 0, 1, 0, 0, 0. Again, 1 is on, 0 is off. So, I have 0. In the 2's place I have a 0. In the 4's place I have a 0. In the 8's place, it's on, so I have a value of 8. 16's place is 0. 32 is on. 64 is off. And 128 is on. Again, I simply add these values across, and I come up with 128 plus 0 plus 32 plus 0 plus 8 plus 0 plus 0 plus 0, and the end result of that is 168. Now this third octet is pretty easy, but I'm going to go through it anyway. I have 0, 0, 0, 0, 0, 0, 0, 1. Sorry about that, 0. And again, all these states are off, and this one's on, which equals 1. Add that up, and it's 1. I'm going to go through these two a little bit quicker than I did earlier. 253. I'm going to have a representation of 1, 1, 1, 1, 1, 1, 0, 1. Add all these up because it's 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 0 plus 1, and I come up with a value, a decimal value, of 253. That's as easy as it is taking my decimal and my binary forms and representing the same numbers with those two different forms. Let's take our results and show them in a bit of a cleaner format. That got kind of cluttered, so here we go. Our IP address 192.168.1.253 is shown in the binary representation as 192.168.1.253. Now before I can show you how to take this binary number and divide it into the two portions that we need for our addressing, which are network, which is the equivalent to the city, and host, which is the equivalent to the street on our envelope, we have to discuss the different classes available in an IP address. And here you see the three we're going to talk about: Class A, Class B, and Class C. There are two more classes, but they're beyond the scope of the CCNA and not used that often anyway. Let's start with Class A. In Class A, we're going to have a range of 1 to 127. What do I mean by range? What I'm talking about there is this first octet, that value has to be between 1 and 127. How do I make that happen? I have a rule. The first octet rule in the Class A address is that the leftmost bit has to be set to 0, and that's this bit right here. That has to be a 0. For that once that's a 0, I can have all bits off except for this one. As we see here, all zeros, and this one on, which is 1, shows the low end of our range. Or I can have this bit and all others behind it set as 1, which would be 64 plus 32 plus 16 plus 8 plus 4 plus 2 and plus 1. This would equal 127. That's the high end of our range. Alright, let's look at the default mask. The default mask is 255.0.0.0. Now when I talk about a mask, this is the tool that we're going to use to derive the two parts that we need. So this is going to be very important. Alright, this default mask has 8 bits in the mask. You'll hear that commonly referred to as an 8-bit mask. Let me explain why. When I say 255 in the first octet, that is turning on every value in that octet. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals 255, and then the rest are zeros. So the bits in the mask are telling you how many bits are set to 1, and it tells you that number of bits from the left reading to the right. Let's go to a Class B address. Its range is 128 to 191, and that's accomplished by the special rule in the first octet of the first bit has to be a 1 and the second bit has to be a 0. With this rule in place, I can have 128 on, and if all the rest were zeros after that, the value would be 128, which is the low end. Or I can have 128 on, the second off, and every placeholder after that on, and I would have 128 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, and that would equal 191, which is my high end. The default mask for this class is 255.255.0.0. Again, the bits in that mask are 16, and the reason we see that is 8 and 8. Essentially 255 and 255. 8 ones in each octet. 16 bits. Class C address. The range here is 192 to 223. The special rule, first 2 places are 1s. The third place is 0. Here we go here. 128 and 64, add those together equals 192. The rest of the places being zeroed out, that's the low end of our range. If we had these two on, 192, the third off, and the rest as 1s, which would be 192, essentially with the first two, plus 16, plus 8, plus 4, plus 2, plus 1, that would equal 223, which is the high end of our range. Alright, the default mask, 255, 255, 255.0. There's 24 bits in this mask, and it's represented right here. So I didn't illustrate it here because it's down here. 255.255.255.0. Okay, now that I have a solid understanding of the different classes involved in an IP network, I can use the default mask, match that against the binary breakout of an IP address, and come up with the two portions I need, one being the network, again equivalent to the city, and the host equivalent to the street, for routing end-to-end on a network. Let's do this. Alright, the process we're going to use is called the logical AND. It has 4 simple rules, and they're found over here. 1 and a 1 combined equal 1. 1 combined with a 0 equals 0. 0 combined with a 1 equals 0. And 0 combined with a 0 equals 0. Probably even more simply stated, 1 combined with 1 equals 1. Anything combined with a 0, the result will be 0. Now where am I going to combine these different values to come up with the result? And it's right here. I have my IP address and I have my mask. I'm going to come straight down the line and combine values and come up with results. Let's start on the left side. A 1 and a 1 combined is a 1. Again, on the second placeholder here, 1 and a 1 is a 1. A 0 and a 1 combined is a 0. And then this is the same thing for the next, well, the rest of the octet, because all of these are zeros. Then I start here. A 1 and a 1 equals 1. 1 and a 0 combined is a 0. I have two 1s combined. I have a 0 here, two 1s. I have zeros involved in the last three placeholders. Now here I have 7 consecutive zeros. So no matter what the value is here, I know that my result is going to be 7 consecutive zeros here. Now I have a 1 and a 1, and there you see the result. Now my mask is telling me I have all zeros in the last octet. Again, it's a 24-bit mask, and I have 8, 16, 24 bits associated as ones here. So with all zeros, I know that the last octet is going to be all zeros. Now we convert our binary representations into decimal, and we come up with our resulting network address, and it is 192.168.1.0. And how did we get that? Again, the conversion is 128 plus 64 equals 192. 128 plus 32 plus 8 equals 168. 1 equals 1. And then this is all 0, so every value is turned off equals a 0. This is our network address. We're going to show you exactly where that fits in our envelope for our analogy, but before we do that, remember we have a second portion together, and that's our host address. The way we do that is we take our mask, which we had here, our 24-bit mask, and we invert it. Now this is called an inverse mask here, so I'll label it with an I. And simply, in the above mask, everywhere you saw a 1, you'll now see a 0. And everywhere you saw zeros, you will now see 1s. This is how you get the host portion derived from the original IP address. You're going to perform the same function, the logical AND, with its associated rules on the IP address, and this time the inverse mask. So let's do that. I have all zeros in the first octet, so easily enough, my values are going to be zeros. Same for the second, and the same for the third. 2, 3, 4, 1, 2, 3, 4, so 8 there. Now, in the last octet is the only place I have any decisions to make, and we'll go forward with those of 1 and 1 is 1, 1 and 1 is 1, 1 and 1 is 1, again, again, and again. I have a 0 associated here, so it's a 0, and the last value is 1 and 1 combined are 1. So now let's find our host address. It is 0.0.0.253. And I get a decimal 253 by combining 128, 64, 32, 16, 8, 4, and 1. Let's take these values now and plug them into our envelope. And we see that originally we had a source address with a street address and a city address here, and the host and network equivalents here for our inner network. Down below then we have our street address, and the host address, as we saw in the last whiteboard, is 0.0.0.253, and our city address, which in our inner network is 192.168.1.0. Note that we haven't done the same thing for our destination IP address, but it's going to be a very similar technique. The only thing is going to be this third octet now had changed to a 2. So let's go back to our diagram and show that. Here we see our destination address of 192.168.2.253 with a 24-bit mask, because again that's the default mask, now we know, for a Class C address. And here our source was 192.168.1.253 that we have already broken out with the logical AND into the network portion and the host portion. Now instead of breaking that out for the destination address in that slow process, I've already illustrated here on the whiteboard, and we're just simply going to review. Our IP address is 192.168.2.253. We see that representation here. Everything the same as it was in the first whiteboard, except for this has changed from a 1 to a 2. We see our logical AND function with its rules. We take the IP address, the subnet mask, the logical AND result is 192.168.2.0. We take our IP address, an inverse mask, exactly as we did before. The logical AND result of that will be 0.0.0.253. Now we're going to plug those values into our envelope as we did before. What we see here is we have a source address and we have a destination address now with two distinct parts in each address. Here we have a street and here we have a city. The same here, a street and a city. So this should help you now with the point that I drew to a little bit earlier, the fact that 192.168.1.253 was very similar to 192.168.2.53. The only difference was that third octet. And I had stated that that is all we need to make the distinction and still have the result of logical addressing that we desire, and that is a unique identifier for every object within a network. Because here we see our city with a street of 253 and a different city with a street of 253. It's just like if we had Dallas, Texas and Los Angeles, both with, let's say, 987 Main Street, and the street here would be 987 Main Street as well. They still are unique to the point that I can have a message sourced here and destined here, and they're two different objects within our network. Excellent. Now you know how to take a single IP address, use the logical AND function, and derive two distinct parts that are used for end-to-end routing. The first part was the network address, equivalent to the city on an envelope. The second part was the host address, which is equivalent to the street address on an envelope. This arms us with enough information to complete the analogy. We start off with the United States Postal Service and trying to deliver a piece of mail from Mary Jane at 987 6th Street in LA, California to John Smith at 123 4th Street in Dallas, Texas. We had a name, street, and city portion, name, street, and city, on both the source and the destination. So let's look at the routing of this message. I had the message put in my mailbox at this local end. A postman picks it up and takes it to the local post office. The local post office is then going to route over the United States Postal Service backbone to the destined end post office. Let's stop here for a second. What portion in our addressing is used to do that? All we need at this point are the city addresses, because I am in LA, California, and I want to send a message to Dallas, Texas, from this post office to this one. Do I care about the street being 123 4th Street? Not at this point. And I definitely don't care about the name of who's going to receive this message. So the post office routes it to the correct city. Once it's in the correct city at this post office, now I'm concerned with the street address. I look throughout my city and say, where's 123 4th Street, and which postman is responsible for that area. That postman takes it from the post office directly to that residence. At this point, the Postal Service job is complete. If this name is correct or it's not correct, it really doesn't care. It really took care of the routing from this source to this destination with two pieces of information, the network and the host for networking, or in this analogy, the city and the street. Looking at our network diagram now, I have a source, N1, with a host address of 0.0.0.253 and a network address of 192.168.1.0, and you see them here, host and network, trying to send a message to N2 with a host address of 0.0.0.253 and a network address of 192.168.2.0. Here you see the host, here you see the network. Now as before, I am going to take a message from N1 and deliver it, well, above is the local post office. Now it's the local router. Okay, so this will be R1 for the local router. Once it's at the local router, we're going to route over the backbone, in this case the internet, to the distant end router. How does it do that? Just like above, it takes one piece of information. It says, I am at 192.168.1.0, this network, and I want to get to the network 192.168.2.0. And that's where it goes. It doesn't care about the host portion at this point. Once the message arrives at the router, now we're concerned with the host, and it says, who is 0.0.0.253? That's N2, and he sends the message to him. If I were to stop here, these two analogies would map directly. There's only one problem. I have to take a step back for the real-world scenario on the networking side. Alright, let's start with R1, send a message over to a router, R2, by using the network address that we found here. Now that I have that packet, R2 wants to use the host address to send it to N2, and I have the host address right here. The problem is, the rule of networking is these devices will communicate via a MAC address. Remember I said I included this for reference. And I had to finish the communication process from N1 to N2. It is a data link address. We're going to discuss it in more detail on that nugget as far as how it's represented numerically and what its purposes are in more detail. But for now, let's just say that formally R2 has to talk to N2. And to do that, it has to know the MAC address. So what do I know so far? Let's see here. I know that R2 has a MAC address. I'm going to represent that simply by R2. It's much more complex, but for now R2. I know that R2, this interface, has an IP address. It's on the network 192.168.2 dot, and let's make it dot 1. So let's say its IP is here. I know N2 has an IP address, which is 192.168.2.253, and I know the network portion versus the host. What I don't know is, what is N2's MAC address? This packet here I am going to send from the router, broadcast to everybody on this network, and it's called an Address Resolution Protocol, ARP, an ARP packet. And N2 is going to pick this up and answer back saying, you know what, that is my IP address, here's my MAC address, and in this case I'm going to keep it simple. Like I said, my MAC is N2. Once I know that MAC address, now I can finish my delivery of that original packet that arrived here over to N2 via a MAC address. There you have a representation of end-to-end routing using logical addressing at the network layer. Next we're going to talk about fragmentation. I have a surprise for you. In our discussion on fragmentation, we're going to start with an analogy. I know, just kidding. We always do. Alright, let me set this up. I have 30 high school seniors. They're going to take a senior trip from Lubbock to Disneyland. For those of you that don't know, Lubbock is a city in the panhandle of Texas. Alright, we're going to start our trip at the local high school. All 30 students are here. The first leg of the trip, they're going to take via bus. The bus has a capacity of 50 people. So our first mode of transportation poses no problem for our 30 people to ride from the high school to the International Airport at Lubbock. From LBB, they're going to take a flight that has a capacity for 180 people to the Dallas-Fort Worth Airport. Again, this mode of transportation offers no problem for the size of the group that we have. From Dallas-Fort Worth Airport to the LA International Airport, again they're going to take a flight, capacity of 180 people, and it offers no problem for our 30 passengers. Now the last leg of the trip. From LAX to Disneyland, the only mode of transportation I have is taxis. Each taxi has a capacity of 4 people, 4 passengers. What does this mean? I'm going to have to take my original group of 30 and divide them into 1, 2, 3, 4, 5, 6, 7, 8 taxis to make the trip on this last leg from LAX to Disneyland, because that is the maximum capacity that I can afford on my mode of transportation. Now once all 8 of these taxis arrive at Disneyland, this group will form back together, and again I'll have the original 30 that I started out with at the high school. This process happens in the networking world as well. On the bottom here I have a packet of 1024 bytes that I want to send from N1 to N2. I have a network that I have to traverse. Alright, as with our analogy above, I had 30 passengers to traverse essentially a network to get to a destination. Same idea here. On my first leg, I am going to ride a protocol that is known as Ethernet. Ethernet's capacity is 1500 bytes. Now when I say capacity on a network though, that's usually referred to as an MTU, and that stands for Maximum Transmission Unit. So the MTU here is 1500. My packet is 1024 bytes. Fits fine, so I send it over the first leg. It arrives at router 1. Router 1 checks on its interface, looks for the MTU, in this case it's 1500, on fast Ethernet, and says there's no problem routing this packet over that network, so it sends it across. Router 2 receives it, does the same thing. It looks on the interface that it needs to send the packet out on, and it says what is the MTU? It's 1500 on fast Ethernet. I have a packet of 1024, no problem, routes it to R3. R3 checks the interface that it's going to send the packet out on, checks its MTU. In this case, it's 552 on a SLIP network. SLIP stands for Serial Line Internet Protocol. It's pretty much just a low-cost, low-bandwidth solution for packets to traverse over a wide area network. So the problem here, though, is that I have an MTU of 552, which is lower than my packet size of 1024. So I have to divide my original packet into two smaller packets for transmission over this media and this protocol. Now when it arrives at N2, just like in our analogy above, these two packets will be formed back into one packet of 1024 bytes and delivered up the stack to the destination application. The obvious question at this point is, if I divided my original packet into two smaller packets, how were my devices on the network, namely N2, able to keep track of when these packets arrived and when to reassemble? And did I know that I had them all? Were there only two? Were there actually three and I was missing one? Let's find that out by looking at the IP header. Here we have an IP header. We have many fields that we've discussed in the past, but this time we're going to concentrate on the identification, the flag, and the fragment offset fields. When a large packet is divided into multiple packets, the version, the header length, and the type of service should remain the same. The total length can vary though, because each fragment may be, and probably will be, a different length than the original packet. Now, here's where we get into something a bit different. The identification. This is a number that's assigned by the source, which in this case in our analogy was N1, for each packet coming out, and it's incremented by 1 each time a new packet goes out, destined for the same destination, in this case N2. So this will have a number assigned to it. Then our flags. There's two flags that we're going to talk about. There's more than that, but here's the two we're going to talk about. The first one, if it's set to 1, means don't fragment. If it's set to 0, you may fragment. The second bit, if it's set to 1, means there's more fragments to come. If it's set to 0, means there's no more fragments. And then finally, we'll talk about the fragment offset. Basically, that's a counter in 8-byte units that says, since the beginning of the original packet, this fragment is that far off from the original packet beginning. And then the rest of the fields are going to remain the same, except for the checksum. The checksum is a numeric value that takes all the length of the field and the bits that are associated with that, runs them through an algorithm, and comes up with a unique identifier that when the distant end runs that same algorithm should be the same. If not, the data has been altered and this packet should be discarded. So that's going to change because it has to be unique per packet. But everything else here should be the same. Alright, so let's look at this in action. If I have my original packet of 1024 that is divided into two smaller packets, the version, the header length, and type of service will remain the same as they were in the original. The total length will vary because they're different, obviously, than the original. The identification. This number is going to be the same in both packets as it was in the original. The flags. Here's where it gets a bit interesting. In the first packet, the first flag that we can set is either don't fragment or may fragment. That's going to be set to may fragment. The second bit is going to be set to more fragment, so a 1, because there are more to follow. On the second packet, we're going to have the same 0 to begin with because we are allowed to fragment, but here we're going to use this 0 that says no more fragments are coming. Now, when these things are sent, these packets are sent to N2, we're going to reassemble both packets and meld them into one. The reason N2 knew that it had all the packets it needed for reassembly are because the flags field told it there are more fragments coming, or in this case, that there are no more fragments coming, and it used the fragment offset to understand that in 8-byte units, I knew that second packet was this far from the beginning, which, once you do your calculation, that says, hey, that's the last fragment, and there was nothing in between. So as you can see, the mechanics of actually fragmenting packets and then reassembling them aren't very difficult. But let's add a little bit extra to our analogy. Let's say, as before, that we started at the high school. This trip took us to LBB, then took us to Dallas-Fort Worth. This is where I'm going to interject something new. At this airport, all flights were grounded, nothing going out for whatever reason. So you had to go to the Dallas Love Airfield to fly out to LAX. This commute here, or this leg of the trip, was done in taxis. Again, 4 people per taxi, so I had to divide up into 8 units to make this trip. Let's look at the effects in our networked environment when we interject that same type of fragmentation in the middle of our path. Here we have, again, another slip link with an MTU of 552, which is going to result in fragmentation, as it did before. But this is where it's going to differ if we have an analogy here of these people making a trip versus a network. And this is why. As soon as my taxis were to arrive here at Dallas Love, those 30 students would again board a flight and be one packet to the destination. This is not true in networking. These two packets are going to exist as two packets until they arrive at the distant end, and reassembly is going to happen here. That's true in almost all protocols. There are a few exceptions, but none to take note of within the CCNA scope. So the key thing here is to understand that reassembly always takes place at the distant end, trying to keep fragmentation as transparent as possible to the other devices in the network. Transparency is one reason, but not the only. As we see here, let's say that R3 did, for some reason, reassemble these packets into one 1024 byte packet. As soon as it got to R4 and it looked at the interface, and again the MTU was lowered to 552 from the 1500 it came in on, I would have to segment again. So you can see the rework that can be saved simply by, as soon as you fragment, letting those fragments ride the network so that you don't have to reassemble and then fragment again. In this nugget, we have dissected the processes involved in end-to-end routing using logical addresses, and then we diagrammed how network fragmentation is accomplished. I hope this has been informative for you, and I'd like to thank you for viewing.